We already studied LU decomposition. Today, for symmetric positive definite matrices, we get a cleaner factorization called Cholesky decomposition, because apparently matrices behave better when positivity supervises them. LU decomposition writes a matrix as a lower triangular matrix times an upper triangular matrix. It is extremely useful for solving linear systems, which is why computers tolerate it. But if A is symmetric positive definite, LU has extra structure hiding inside it. Cholesky decomposition extracts that structure instead of leaving it on the floor. Here is the theorem. If A is real symmetric positive definite, then A equals L times L transpose. Here L is lower triangular, and its diagonal entries are positive. That positive diagonal condition removes annoying sign ambiguity, because apparently even square roots need adult supervision. For a 2x2 symmetric matrix, write L with unknown entries alpha, beta, and gamma. We want LL transpose to equal A. Multiplying gives alpha squared in the top left entry, alpha beta off the diagonal, and beta squared plus gamma squared in the bottom right entry. So alpha is the square root of the top left entry, beta is b divided by that square root, and gamma is the square root of c minus b squared over the top left entry. Positive definiteness gives these inequalities directly. The first standard basis vector gives a positive top left entry. The vector with coordinates negative b over a and 1 gives c minus b squared over a positive. So the square roots exist. No Sylvester criterion needs to enter wearing a cape. For the general case, use induction. Split A into blocks. The top left entry is positive for a very short reason. The first standard basis vector is non-zero. So positive definiteness gives E1 transpose A E1 positive. That number is exactly the top left entry A. Now force the first column of L. Put square root of the top left entry in the corner, and R divided by that square root below it. What remains is to factor a smaller matrix. The smaller matrix is called the Schur complement. C equals B minus RR transpose divided by the top left entry. We need C to be positive definite. Take any non-zero vector y, and build a vector x whose first coordinate is chosen to cancel the cross terms. This is the algebraic version of sweeping the mess under exactly the right rug. A direct block multiplication gives x transpose AX equals y transpose CY. Since A is positive definite and y is non-zero, this vector x is non-zero. Therefore y transpose CY is positive for every non-zero y. So C is positive definite. The induction can continue. By induction, the smaller positive definite matrix C has a Cholesky factor M. So C equals MM transpose. Insert M into the lower right block of L. The first column was already forced by the top left block and the vector R. Multiplying LL transpose gives A. That proves existence. The diagonal entries are positive because we took positive square roots at every step. This also gives a practical check. If a symmetric matrix successfully factors as LL transpose with positive diagonal in L, then it is positive definite. Indeed, X transpose AX becomes the squared length of L transpose X. Since L has positive diagonal, L is invertible. So a non-zero X cannot be sent to 0 by L transpose. And the squared length is positive. That proves positive definiteness. Conversely, during exact Cholesky decomposition, if a required positive square root fails, The matrix was not symmetric positive definite. The matrix has failed its health screening. Cholesky decomposition is the positive definite version of triangular factorization. Symmetry turns the upper triangular factor into a transpose of the lower one. The proof uses induction and the Schur complement. And in practice, trying Cholesky decomposition is itself a useful positive definiteness check. Next time, we use it to create correlated Gaussian random variables.